chromium, during solidification of these alloys, we see that the tin actually segregates to those eutectic colonies that you saw in the silicon chrome disilicide alloys. So what we would expect is we would achieve the same type of toughening within these eutectic colonies, but we'd actually achieve other toughening mechanisms at the colony boundaries, such as crack blunting or crack arrest, which is actually shown by this Fischer indentation on this alloy on the right-hand side. Another criteria of this project are that the alloys be castable. And in my project, I particularly chose the induction melting process to produce these alloys. But there's other casting methods that really should be studied as a means to produce these materials. For instance, die casting, sand casting, and investment casting. And a cost-benefit analysis should be done to compare these different casting techniques, as well as to compare these casting techniques to powder processing techniques used to make ceramics. And actually, as a proof of concept, we actually investment casted MIT medallion, shown over here, of our alloy. This is a silicon chrome vanadium alloy. And what we see is that we could actually achieve a very high quality of detail in these materials quite simply by using an investment casting process. And this sort of detail would be very difficult to achieve using some of the powder processing methods used to make engineering ceramics. And finally, my project really only focused on the wear properties and fracture properties of our silicon disilicide alloys. However, there are other properties that need to be considered which are important in both processing and application of these materials. For instance, we may want to measure kinetic properties such as diffusivities or atomic mobilities and combine that with our thermodynamic data in order to simulate phenomena such as microsegregation during solidification or homogenization or coarsening of these alloys, which again are very important for both processing and operation of these materials. Another property which is very important to measure is the fracture strength of these composites, and maybe even more importantly, the variability in the strength, or the Weibull modulus. And it's been found for ceramic materials that by improving the fracture toughness of ceramics actually leads to an improvement in the fracture strength and a decrease in the strength variability due to the increased flaw tolerance of these materials. So it'd be interesting to note if the improved fracture toughness properties which we measured for our composites also leads to an improvement in fracture strength and an improvement in the strength variability, or the Weibull modulus. And finally, all of the tests that I did in my project were done at room temperature, but of course, in many potential applications, these materials may experience elevated temperatures, and so we want to study some temperature-dependent properties, such as the brittle ductile transition temperature of our alloys, the wear resistance of our alloys at elevated temperatures, since it's known that elevated temperatures tend to accelerate wear in many engineering materials, and finally, the oxidation resistance of these materials, of our alloys. And with that, before I address any questions, there are a ton of people who I would like to thank. First and foremost is my advisor, Chris Hsu, who's been just an amazing, amazing mentor over the last few years of this project, and I could truly say that I aspire to be that type of mentor advisor for other people in my career, or at least a fraction of how good he is, truthfully. Of course, the rest of my thesis committee for all of their constructive insight in this project, including Professor Thomas Eager, Professor Ron Ballinger, Professor Fred McGarry, and Dr. Vazgen Shamamian, who's actually from Dow Corning. I also, of course, need to thank the rest of Dow Corning Corporation for funding this project, and of course for their continued support throughout the entirety of this project. And again, I just want to particularly mention Dr. Dimi Katsoulis, who from Dow Corning, who was involved in many of the early research discussions in this project. I want to thank Dr. Larry Kaufman, who actually personally came to MIT to teach me the CalFan method. I would have definitely not been able to do that work without him. And there are a bunch of MIT faculty who I need to thank. Mike Tarkanian, who's in the back, for all his help in the foundry and for the casting of these alloys, who really put his life on the line, pouring those hot materials. So he deserves a gold heart, Purple Heart, something like that. Yinlin Si, and Don Galler, who's also here today, for his help in the in situ SEM setup and those experiments. He was a huge help. A year up of mine who has since graduated, his name's Ryan Brenneman. He actually helped me with the investment casting of those MIT medallions you saw at the end of this project. Of course, all of the SHU research group who's here today, and for those who've graduated, for all your help through my years here, and you've truly made my work experience, you know, an amazing time at MIT these past few years. And finally, last but not least, my friends and family, a lot of who are here today. So I'll point a few out. We have Tim Rupert, who's actually part of the research group, Brian Homing, of course my girlfriend Brooke, who has supported me even though she had to take 5-hour Greyhound rides every other week to be here. My family, a bunch who are here, Uncle Mike, Aunt Karen, Grandma Lee, my brother Andrew, and of course my parents, Robert and Elise Fischer, without whom, you know, everything they've given up for me over my past 27 years, not just the 5 years here, I could really, truly, and honestly say I wouldn't be standing up here today. So with that, I'll address any questions that you have. Thank you.